All right, this is the fourth lecture of the condensed matter course. Where we left off last time, we were talking about the free electron, or the Sommerfeld theory of metals. Free electron, or Sommerfeld theory of metals. And what Sommerfeld was doing, he was more or less following Drude's idea that a metal is just a gas of electrons, and he was trying to apply kinetic theory. The only thing he was doing differently is he was respecting Fermi statistics. He was keeping track of the fact that you can't put two electrons in one eigenstate. And in last lecture, we derived that the Fermi wave vector is related to the density of electrons by 3 pi squared n to the 1/3, where n is the electron density. And unfortunately, in the last lecture, I made an error. I mistakenly called this thing the Fermi momentum. It's actually the Fermi wave vector. And I even wrote it on the board incorrectly. H bar times the wave vector, kf, is the Fermi momentum. Sorry about that. From the Fermi wave vector, we can get the Fermi energy in the usual way. EF is h bar squared kf squared over 2m, which we can substitute in our expression for the Fermi wave vector. H bar squared over 2m, 3 pi squared n to the 2/3. This is a rather important relationship that we'll use again. But what's important to realize here is the bigger the density of electrons you have, the bigger the Fermi energy. And in a typical metal, like iron or lead, the density of electrons is really big, a couple of electrons per atom. And you have a whole lot of atoms. There's very high density of atoms, an atom every couple angstroms. So the Fermi energy gets to be enormous, on the order of 80,000 Kelvin, or even bigger sometimes. Now, in this lecture, what we're going to aim to calculate is something that we discussed earlier, the heat capacity. And from experiment, we know the heat capacity for metals at low temperature takes this form of T cubed plus T, whereas this T cubed term comes from vibrations, or Debye theory. We discussed that already. And this gamma T term is special to metals, and in fact is the heat capacity of the electrons. So it's this gamma T term that we're going to be interested in today. Now, before we actually do this, we need to do a little bit of preparatory algebra. In particular, we're going to need to take sum over eigenstates and put it into a more workable form. And the eigenstates in this case are going to be e to the plane waves, e to the I k dot r. And again, since we're writing this as exponentials, what we're implicitly doing is we're putting the thing in a periodic box, Born von Karman boundary conditions, periodic in all directions, so we can work with exponential plane waves instead of sines and cosines. What we'd like to do is we'd like to take the sum over eigenstates, and we would like to convert it into an integral over energy, g of energy, where g is now a density of states. This is very similar to what we did when we did Debye theory. However, we're going to do something slightly different here. Slightly different, we're going to remove a factor of the volume from the density of states. So this is now density of states per unit volume. And we do this because it's conventional to do so, and it's convenient to do so. And if you didn't notice it before, conventional and convenient come from the same word. So it's both of those things. It just happens to be handy to do so, so we're going to do it. At any rate, the definition of this density of states is that g of e dE is the number of states per unit volume in this case, volume with energies between epsilon and epsilon plus d epsilon. Very similar to what we had for Debye theory before, when we were thinking about density states per frequency. Now, the general idea, again, is that we're going to take the sum over all the eigenstates, and we're actually going to convert that sum over individual eigenstates to an integral over energies times the number of states at each energy. Just a different way of writing it that makes your life a lot easier. All right, so what are we going to do here to get from the sum into the integral? Well, first thing we're going to do, sum over eigenstates, is really a sum over k. But it actually has a factor of 2 out front because there are 2 spins per k spins. An electron can be spin up or it can be spin down with the same wave vector. Then we're going to do the same manipulation we did with the Debye theory. Leave the factor of 2 out front. We're going to replace the sum over k with an integral d3k over 2 pi cubed. This is the way sums get converted into integrals, and we'll make that replacement many times this year. A sum over k becomes a volume times the integral d3k over 2 pi cubed. And then, since we're thinking about an isotropic system, we can convert the integral over 3 Cartesian directions into spherical polar coordinates. So we have 2v over 2 pi cubed. And then we have an integral 0 to infinity 4 pi k squared dk, where the 4 pi k squared is the usual. Well, 4 pi is the directions on the sphere. So it's the usual spherical polar coordinates. And this is a pretty good result, but really we'd like to write this in terms of energies, not in terms of wave vectors. So we'll use epsilon is h bar squared k squared over 2m, or I guess we could write that as k is square root of 2m over h bar times epsilon to the 1/2. And in particular, that would give us dk is the same fact, well, it's a 1/2 times the same factor, square root of 2m over h bar times epsilon to the -1/2 d epsilon. Then if we plug these things into here, what we then get is, okay, so we now have 2 volume. I'll pull out the 4 pi, and we have the 2 pi cubed downstairs. Then we have an integral 0 to infinity d epsilon, and then putting in those factors for the k squared dk, we get 1/2. There's 3 of these factors, 2m, square root of 2m over h bar cubed, and then epsilon to the 1/2. So this looks almost like what we want. It's almost the integral of g of e dE. So we then identify, well, okay, so I'll just write it out again. So this thing is integral 0 to infinity g of e dE, where we've defined g of e to then be 2m to the 3/2 over h bar cubed times 1 over 2 pi squared times epsilon to the 1/2. So density stays proportional to epsilon to the 1/2. And this is a perfectly good answer, but it's actually convenient, and therefore conventional, to convert this factor of 2m over h bar cubed into something that looks a little nicer. And the way we do that is by using this equation here. So that equation there, I'll actually maybe write it over here. If I take that equation to the 3/2 power, I get EF to the 3/2 equals h bar cubed over 2m to the 3/2 times 3 pi squared n. Did I do that right? I think I did that right. Okay. And then you'll notice that I can turn this around, or make it upside down. 2m to the 3/2 over h bar cubed is then 3 pi squared n over EF to the 3/2. And this factor here is this factor here. So plugging that in, we get g of E is then, what? It's 3 pi squared density. I know this is a lot of algebra. It's a big algebra day because it's a Monday. 3/2, 1 over 2 pi squared, epsilon to the 1/2. And then canceling a few things, we get our final result. G of epsilon is 3/2 density over EF times energy over EF to the 1/2. Did I make any mistakes? Does that look right? Anyone object? Look good? All right, this is going to be something fairly useful. And in particular, it's useful to look at the density of states at the Fermi energy, which is just 3/2 density over EF, which I think is something that you're asked to derive in their homework as well, the first homework set. And I'll give you a quick hint that I think there's an easier way to get there than what I just did. But you know, if you can't figure it out, you can just follow this. But there's a cheaper way. But this is sort of the more, you know, it's the more direct route. The other way is sort of sneakier. Anyway, see if you can figure it out. OK, at any rate, now we're going to try to use this result, figure out, we know the density of states here, density of states per unit volume, and we're going to try to use this to figure out the heat capacity of the electrons at low temperature. Now, there's always more than one way to do something. There's the right way, and there's the cheating way. And what I'm going to do is I'm actually going to explain how the right way is done, and then we're going to cheat. And the reason we're going to cheat is because the right way is algebraically really horrible, and it's really hard to get any intuition just by doing algebra. We just did enough algebra, and I promise you doing it the right way is 3 times more. So furthermore, the actual calculation is so algebraically complicated that you'll never be asked it on any exam at Oxford. And that is, I mean, I can't 100% guarantee it, but I can 99% guarantee it. So because of that, we're going to just do it the cheating way, which gives you the intuition for what's going on and avoids a lot of algebra. But it's worth knowing at least how you would go about it if you really wanted to be honest. So if you really wanted to be honest, what you would do first is you would write an equation for the number of electrons in the system. And we wrote this equation before last time. It's the sum over all eigenstates of the probability that each eigenstate is filled. And that probability of an eigenstate being filled is the Fermi function of beta, the inverse temperature, times energy of the eigenstate minus mu, the chemical potential. And being that we just derived the density of states, we can rewrite that as an integral, well, volume times the integral from 0 to infinity of the density of states per unit volume times the Fermi function. So it's exactly the same expression, d epsilon, exactly the same expression, except instead of writing sum over eigenstates, you integrate over all energies, the number of states at each energy, and of course, you're always integrating the probability that a state is filled. Is everyone good with this? Yes? Yeah, OK, good. Now, this equation here, you can think of it in 2 different ways. One way is if you could fix the chemical potential and you knew the temperature, it would tell you how many electrons you have. But more often than not, it goes the other way around. You know the number of electrons you have in your system because you know how many atoms you have or something like that. And you know the temperature, and it enables you to figure out the chemical potential. So it's sort of an inverse relationship. You know this, and so you can figure out this in principle, although it's algebraically messy to do so. But in principle, it would allow you to figure out the chemical potential, given that you know the number of particles and you know the temperature. Once you had the chemical potential, you could write an expression for the energy in the system, integral, again, integrating over all states. But now you integrate the energy times the probability that a state is filled. OK? So instead of just counting the particles, you count the particles times their energy to get the total energy in the system. So you find the chemical potential first. You then find the energy. Once you know the chemical potential, then therefore you would know the energy as a function of temperature. You could differentiate that to get the heat capacity. So in principle, from this kind of argument, you could get the heat capacity if you could do these integrals. The problem is that these integrals are really nasty, and that's why we're not going to do it this way. Instead, we're going to make some assumptions which aren't quite right. But to see what the assumptions are, let me first draw a diagram. This is the Fermi function again, which we drew last time. It's NF, 0 temperature, NF goes from 1 to right here, EF, 1 to 0. So this is t equals 0. And then at finite t, the Fermi function smears out a little bit, like this, is t greater than 0. OK? This all looks familiar, I hope. OK, incidentally, I believe this full calculation, I think you actually did it last year in your stat mech course, or at least the lecturer did it. And you probably remember that it was pretty awful. and it's hard to actually remember anything about the intuition of what's going on if the algebra is really awful. So we're going to try to do this in a cheaty way that is going to give you the intuition a lot better. So the one thing we're going to assume, which isn't quite right but is pretty close to right, is that the chemical potential doesn't actually change as a function of temperature. Now, it does change as a function of temperature because of this equation, but it only changes a little bit. Why is it only changes a little bit? Well, if you look at the Fermi function here, you can imagine as you raise the temperature, what's happening here is some of the states here that were filled now move to here. So there were some electrons here, they empty out, and they fill these states up here. Okay? Now, if the number of states that empty out and the number of states that filled are equal to each other, the chemical potential doesn't have to move at all. You would keep n constant, keeping the chemical potential constant. Now, in truth, you have to adjust the chemical potential a little bit as a function of temperature to keep the total number of particles fixed, but you don't have to adjust it a lot. Basically, the chemical potential stays almost exactly the same. So we're going to make this assumption. Where do I write it? Maybe here. Assume mu is independent of t. It's not quite right, but it's not too bad an approximation. Once we have that, well, actually, once we had that, we could take this equation here and then say, OK, let's plug in mu fixed as a function of temperature, and then we could calculate the energy as a function of temperature here, assuming mu is fixed, differentiate it, and get the heat capacity. But even that's too complicated because this integral is just really nasty. So we're not even going to do that. We're going to do something even simpler. So what we're going to do is we're going to write the energy at some temperature T is the energy at T equals 0 plus two very approximate things. Approximate thing 1 is number of electrons that can get excited. That can get excited. And thing 2 is times amount of energy each absorbs. So you imagine starting at 0 temperature, and then you turn on the temperature, and then there's some number of electrons can get excited. Each one absorbs a total amount of energy, some amount of energy, and the product of these two roughly gives you the total amount of energy that you've increased your system by. Sound reasonable? Yeah? Yes? Yes? Is it reasonable? It's roughly true. You know, it's roughly right. OK, bear with me. OK, so now all we have to do is we have to figure out what are these two factors. So the number of electrons that can get excited. So this is sort of the interesting piece here. The number of electrons that are excited is roughly number of electrons within kBT of EF. Why? So you have to be, so this range here is about kBT. And you have to be within this range of EF in order to get excited. Because if you're farther down here somewhere, you can't get excited. It's hard to get excited, right? So you can't get it. That was supposed to be funny. An electron in the state down here can't get excited at all because all the states it would get excited into are already filled. So it can't move. It's just stuck in that state, and it's going to be frozen there unless you turn the temperature, huge so it could jump all the way up to here. Okay? So it's the number of electrons within kBT of EF. And how many is that? Well, it's basically the density of states per unit volume at the Fermi energy times the volume. So this gives you the total number of states per unit energy at the Fermi surface times kBT. So we're taking the number of states per unit volume at this energy, and we're multiplying it by this range to give you the total number of states within kBT of EF. Then we take that factor and we multiply it by the amount of energy each electron absorbs, which has got to be roughly kBT. kBT times kBT here. So some electron from down here within kBT of the Fermi surface got excited up to here by absorbing about kBT of energy. And then, to try to be a little bit more honest about the fact that we're cheating, completely cheating here, well, I'm going to add a fudge factor. So E total is E at t equals 0 plus those factors there, which we just derived. So it's V G at EF times KBT squared. And then the fudge factor is we'll call gamma twiddle over 2. And gamma twiddle is just our admission of guilt that we didn't do a real calculation. And we know we're going to get the answer wrong by some factor of order 1. So gamma twiddle could be 2, it could be a half, it could be pi, it could be 2 pi, but it's not going to be 100, it's not going to be 1,000, it's not going to be 0.01. Okay? So it's some number of order 1, which is our admission of guilt that we didn't actually do the real calculation. Okay? Once we have this expression, we can, of course, differentiate it. CV d E dt, which is, this is why I put the factor of 2 in, so it goes away when you differentiate. Isn't that clever? So KB, and then G at EF, and you're left with KBT. And in fact, we already derived G at EF over there, so let's plug it in. 3/2 n over EF, and we're also going to use, well, maybe I'll put it here, convenient, conventional, that the density times the volume is the number of particles. So when I multiply this factor by, well, I'm going to write it out here. So I multiply 3/2 n over EF here by V. The V and the small n give you a big N. And we'll get this gamma twiddle factor times 3/2 big N KB times KBT over EF. Okay, so that's our final result. And actually, if you did the calculation really honestly, you would discover that gamma twiddle is pi squared over 3. And I'm sure you're not going to be held responsible for knowing that, but just for our general edification, that's what the number actually happens to be. If you really want to see how to do this calculation, you can go back to your StatMech notes from last year, or you can, it's in a lot of books and so forth. I hate it when people say, it's in a lot of books. But trust me, the algebra doesn't really teach you much. If you really, want to see how it's done, you can work through it. Sommerfeld did work through it. He got the right answer. But we're not going to be, held responsible for it. Anyway, a couple of important things about this result. First of all, it's linear in temperature. And the reason it's linear in temperature comes fundamentally from the fact that only electrons near the Fermi surface can absorb energy. Okay? When temperature goes to 0, the range of electrons that can get excited near the Fermi surface drops to 0, and you lose your heat capacity altogether. Okay? So, and in fact, this is what we wanted experimentally. We wanted to get a heat capacity that is linear in temperature. So that's the first good thing about this. Another thing that's really nice about this expression is you'll recognize this piece here as the classical result for a monatomic gas, 3/2 NKB. Sounds familiar, right? And then it's multiplied by this factor here, KBT over EF, which is what? It's tiny. It's like room temperature, 300 Kelvin over 80,000 Kelvin. Tiny, tiny, tiny amount. So you have only, again, coming from the fact that only a few electrons are participating in the heat capacity. So this result, Sommerfeld went and he said, OK, this is my new prediction for what the heat capacity of a Fermi gas should be. And so let's compare it to experiment. So, well, OK, so let's write it as gamma T. All of those constants get absorbed into the overall gamma. And he's going to, well, OK, if you want a real theory of how much heat capacity a particular metal should have, you need to know what the density of the electrons in the metal is, so you can calculate EF. But he did the usual thing and said, OK, let's assume 1 electron per atom, the same way we'd done before. And if you do that, then you write out gamma, gamma for the experiment divided by gamma from the theory, and with the theory assuming 1 electron per atom. For lithium, we get 2.3. For sodium, we get 1.3. For potassium, 1.2. Copper, 1.5. This is a pretty good agreement. It's extremely good agreement considering that the classical theory, what Giroud had done, the 3/2 NKB result is too big by a factor of 100. And all of a sudden, we're getting results which are really pretty close to the right answer. And the reason we're getting results that are close to the right answer is because we're treating Fermi statistics more honestly now. Okay? Well, we didn't treat them at all before. And now Sommerfeld said you put in the Fermi statistics, you get the heat capacity right. Okay? Now, he went on and said, in fact, with this newfound understanding of what's going on, Fermi statistics being important, we can fix some of the problems with Drude theory. And one of the things that you recall from Drude theory, one of the things we calculated, which we actually got pretty close to right, was the thermal conductivity. Thermal cond. We had an expression, this kinetic theory expression, kappa, the thermal conductivity, 1/3 density CV, heat capacity per electron. Then it was V squared times tau, the scattering time. And Drude, in this expression, Drude used these things that we don't like anymore. The CV is 3/2 kb, the classical result. And he also used the classical result for V squared, 8 kBt over pi m. So the combination CV times V squared, which actually enters in the thermal conductivity, it has the value 12 over pi, kBt over m. Right? Okay, now Sommerfeld said both of those results are wrong. So let's use the right results. So his result was CV is, he has the pi squared over 3, and then 3/2 kb, the classical result, and then kBt over EF. And then he said, okay, and V squared is not given by the classical kinetic theory result, but should instead be given by Vf squared, the Fermi velocity squared. And just make things a little bit simpler, we can write EF as 1/2 mass times Vf squared. Put those together, we get some cancellation. Again, if we look at the factor CV times V squared, we get pi squared times kBt over m. So in fact, what we discover, it's not too far from the Drude prediction. In fact, Drude over Sommerfeld is what? It's 12 over pi cubed or something? It's about 1/2. So it gets pretty close to the same result. Did I get that right? 12 over pi cubed? Yeah, I think so. So you get pretty close to the same result, which is good because we like the answer for the thermal conductivity that we got in Drude theory. It satisfied this Wiedemann-Franz law that was known to exist experimentally, and so we didn't want to ruin that. And in fact, Sommerfeld theory doesn't ruin it. Two mistakes: the heat capacity and the velocity cancel each other out exactly. Well, not exactly, but pretty close to exactly. But there were other things that Drude got completely wrong. One of them was the Peltier coefficient, which, let's see, what was Peltier coefficient? I think I left it over here. Yeah, okay. It was Peltier coefficient pi is CV times T over 3 times minus E. And in Drude theory, this came out 100 times too big, more or less. But now, if we plug in the new value of CV, which is 100 times smaller, we're all of a sudden getting things that start to look right. Okay? So this is good. So Sommerfeld was pretty happy with this result. But unfortunately, as with all things, he introduced a new problem. What's the new problem? Well, okay, let's go back and remember the conductivity expression, Ne squared tau over m. That's still the same result in Sommerfeld theory. It will give you the same prediction. It better be the same prediction because we have the ratio of, we wanted to get the right ratio of thermal conductivity to electrical conductivity, and we didn't change the thermal conductivity much, so we better not change the electrical conductivity much either. So more or less up to maybe a factor of 12 over pi cubed, we expect that the conductivity should be given by this expression. So probably this expression is a good one to stick with. And we don't know tau, but we can measure sigma. measure this, measure sigma to get tau, get this, get tau, and then from tau, we can calculate the mean free path, lambda, mean path, scattering length, which would be v times tau. Now, in Sommerfeld theory, we would probably replace this with vf times tau, because the electrons are moving around at speeds close to vf. And the problem is that vf is close to the speed of light. Well, not close to, but it's 1% the speed of light. It's extremely fast, which means the mean path is extremely long. So lambda is huge. Unreasonably big. How big? Well, at room temperature, at T room, lambda can be, say, 100 angstroms. May not sound enormous, but at low T, lambda can be a millimeter. And again, that may not sound huge to you, but you have to think about how many things the electron has to go past before it scatters. Well, every angstrom, there's another atom, or every 2 angstroms, there's another atom that the electron could bump into. So here it goes by 100 of them, here it goes by 1,000,000 of them before it bumps into something. So what can it have bumped into? It could have bumped into the nucleus, it could have bumped into the core electrons, it could have bumped into the other free electrons in the free electron gas that are running around, and for some reason, it doesn't bump into any of them. Really, really strange. And this is something that we're not going to answer until much later in the term when we study Band's theory of solids. So for now, the unreasonably long mean free path is just a puzzle that we're going to have to deal with. So this was something that troubled Sommerfeld back then, troubled a lot of people back then. But, Sommerfeld was brave, and he decided, what else? We did pretty well over here, understanding the heat capacity, the thermal conductivity, the Peltier coefficient. What else can we calculate that we might be able to get right, not worrying about this particular little problem? And so now we're going to take a little bit of a out-of-order detour and discuss a little bit of magnetism. Now, the last couple lectures of the year, so week 7, are entirely about magnetism, so this is a little bit out of order. But I think it fits in here well because it really is based on exactly the same business that we just went through. And the particular type of magnetism we're going to study is what's known as Pauli paramagnetism of free electrons. Now, Pauli, of course, you all know him. He was the exclusion principle guy. He's also, people said he was the most arrogant man who ever lived. He used to tell his students that it was okay for them to make a mistake. Of course, he never made a mistake himself, but it was okay for his students to make a mistake. So that was typical of him. But he was a very great scientist, and he actually did this calculation before Sommerfeld did his work. So a lot of this maybe should be called Pauli theory, not Sommerfeld theory. At any rate, paramagnetism, what is that? So what one does is one applies a magnetic field to your system, and you measure the magnetization that comes out. The proportionality constant is chi over mu naught. Mu naught here is just the usual constant, the permeability. I'm probably spelling this wrong. Permeability. Is that right? Maybe that's right. Anyway, that's the constant that shows up on your data sheet, some fundamental constant. This chi here is is known as susceptibility. So this equation defines chi. Paramagnetism means chi is greater than 0. So in other words, you apply a magnetic field to the physical system, and it develops a magnetization in the same direction as the field that you applied. So how are we going to address this? Well, first thing we have to do is we have to write a Hamiltonian for our electrons. We'll write p squared over 2m, the usual kinetic term, plus a coupling of the electron spins to a magnetic field. You may have seen this in the atomic physics course last term. So sigma here is the Pauli spin operators, and it has, importantly, it has eigenvalues, eigs plus or minus 1/2. B is the magnetic field. Mu here is the Bohr magneton. Fundamental constant. is E h bar over 2m. And numerically, it's useful to keep in mind that that number is somewhere around a Kelvin per Tesla of energy. G here is the G factor. And for electrons, the G factor is typically, well, a free electron, out in space, the G factor is 2. So we're just going to use 2. And that's going to prevent us from having to write G and G twiddle and get confused, because we're already using G for density of states because it's conventional, therefore convenient. OK, anyway, if you're at this point, you might be wondering, if you took the relativity course last term, why is it that I wrote p squared over 2m if we have magnetic fields, where you might have expected that instead you should have p plus ea squared over 2m, where a is the vector potential. Does this look familiar from? Yeah. OK. So the ea that shows up in the kinetic energy, this is the piece that makes the electrons curve. If you leave it out, the electrons don't curve. OK? We're going to leave it out. The reason we're leaving it out is, well, twofold. First of all, because it's hard to treat. It's actually a rather complicated calculation to deal with how much the electrons curve and what that does to the magnetization. But the better reason to leave it out is because the influence of this term, this EA term, is actually less than the influence of the coupling to the spin. The coupling to the spin is actually more important than the coupling to the actual physical motion of the electron. So we're going to treat this term, we're going to throw out this term. Okay? If you really want to know the answer, in fact, what this term will do is it will change the answer by a third in the other. So we'll get, if you put this in, it actually has the opposite sign as the result we'll get here, and it's only a third as big. So it will make the final result 2/3 the final result. It's not important. We're going to ignore this for now. We're going to keep this. All right. So ignoring the EA term, just keeping the spin term here, what we have is that the energy for an electron with wave vector k and spin up is ek naught plus mu bb, whereas energy spin down is ek naught minus mu bb, where ek naught is h bar squared k squared over 2m, the usual free electron energy. So the idea is that when you apply a magnetic field, the upspin electrons become more expensive, the downspin electrons become less expensive, and so what's going to happen is some of the upspin electrons are going to flip over to try to become downspin electrons because that would lower their energy. However, they can't all flip over because a lot of the states are already filled, and they can't flip over into states that are already filled. So you're going to get some of them flipping over, but not a lot of them. Okay? So I'm going to run out of room here pretty quickly. So let's start with b equals 0, and do the whole calculation. We'll do it at t equals 0. That's OK, because t is much, much less than tf. So it's pretty close to t equals 0. And if we calculated the number of spin-up electrons, or the density of spin-up electrons, that's the number of spin-up electrons divided by the volume, at b equals 0, it should be the same as the number of spin-down electrons. Ups and down are symmetric in that case, v. And we can write that as integral 0 to infinity dE. Actually, we'll cut off the integral at EF. We're going to count only the electrons that are the states that are filled, g of E over 2. And I put in the divided by 2 because here we're writing an expression for only the spin-ups or the spin-downs, not both of them. G of E, the density of states that we calculated, was the total density of states of both spin-ups and spin-downs. Okay? So let's draw here density of states, G of E for spin-ups here. This is E. And you'll recall somewhere on the board, I think I scrolled it off the top. Oh, well, maybe it's over here. Yeah, here it is. The G of E is proportional to e to the 1/2. So this thing looks like a parabola that way. And then we can also plot G of E for the spin downs. It's going to look exactly the same for the spin downs, like this. And they both get filled up to the Fermi energy, EF. This is in zero magnetic field, EF. Now, when we add the magnetic field way up there, the spin-up electrons are going to become more expensive. These guys are going to get shifted up in energy by mu BB. And the spin-down electrons are going to become less expensive, so you're going to get shifted down in energy by mu BB. Actually, maybe I should arrange some things here. So some of the spin-ups are going to get going to want to turn over to become spin-downs to lower the energy. So let's draw that. What happens? See if I can do this. So once we add, so this is for b equals 0 in this picture. B equals 0 over here. Let's try to draw b not equal to 0 over here. So here we have energy. Here we have g for the spin-ups of E. And here we have g for the spin-downs of E. And what happens is that these guys got shifted up in energy like this, where this distance here is mu b times b. And these guys got shifted down like this by this much mu bb. Okay? And then we fill them both up to EF. Here, this is EF. This is EF. So you see that some of the ones that were spin up, these guys here, emptied out and filled these states here. Is that clear how that happened? So these states here got pushed up in energy above the Fermi surface, so they emptied out, whereas these states here got pulled down in energy, so they filled up. Okay? Is that clear? I know this gets a little bit confusing. Bear with me. So if we want to write an expression for the spin-up density, we can write integral from 0 to EF minus mu bb. Because actually, we only want to integrate up to here. Because in finite, only this region, not this region here, because once we add magnetic field, it's only this region here. It's only the smaller region here that's filled up. These guys have now emptied. dE of g of E, I guess over 2. Whereas the number of spin downs is integral from 0 to EF plus mu bb, dE g of E over 2, because we want to integrate all the way up to here, since those have been pulled down in energy. Is that clear? All right, so we're almost there. So now what I want is I want to calculate n down minus n up, which is integral dE from EF minus mu b to EF plus mu b of g of E over 2. And then we can just, since this is over only a little small sliver of energy, we can use the rectangular rule to calculate that integral, and we get 1/2 g of EF times 2 mu bb. Cancel the 2's if we want. Okay, let's write it out. G of EF times mu b times b. And then, finally, the magnetization, which is what we're looking for, the magnetization is mu b. Each electron has a magnetization of has a magnetic moment of 1 Bohr magneton. And then we have the density of spin downs minus the density of spin ups will give you the magnetization. And if you want to know why the sign comes out this way, why it's downs minus ups, not ups minus downs, it's because the charge on the electron is negative, meaning the spin of the electron actually points opposite its magnetization, which is pretty confusing. But that's what we have to deal with because the sign of the electron is negative. OK, so we'll plug in n up minus n down. So we'll get g EF mu b squared times the magnetic field. And you recall the definition of susceptibility, chi over mu naught magnetic field. So we identify the susceptibility, the Pauli paramagnetic susceptibility is mu b squared mu naught g at EF. And that's our final result. Again, we can take this result, compare it to theory over chi experiment, and do it for various different things. For lithium, that ratio is about 2.5. For sodium, it's 1.8. For potassium, it's 1.6, which is pretty good agreement. Now, if we were thinking about classical particles, classical monatomic gas, then, in fact, when you applied a magnetic field, nothing would stop them all from flipping over. They would just go right into their, the flip down state, because that would be lower energy. And the only reason they don't all flip over is because of Fermi statistics. Fermi statistics prevents them all from flipping over because some of the states are already filled, and so you get a finite susceptibility, whereas the classical calculation would predict an infinite susceptibility. So this is pretty good. We're getting results that are within a factor of 2 or 3 of the actual experiments. So this is more or less all we have to say about Sommerfeld theory. So let's summarize a couple things. Successes of free electron theory, which means Drude plus Sommerfeld. Drude plus Sommerfeld. Well, okay, a couple successes. We got the heat capacity right. We got the conductivity good. The thermal conductivity good. The ratio of those two are good. The Peltier coefficient is in the right ballpark. The susceptibility. And there's actually many, many other things that you can calculate that you'll get right. So the free electron picture is actually pretty good. However, there are still some problems that we're going to have to deal with. One is that, as I mentioned earlier in this lecture, lambda seems too big. Too big. That's a big problem. Having a mean free path of 1 millimeter just seems completely unreasonable. We used that the density of electrons should be 1 electron per atom. And we had some intuition why we should do that, because, well, there's a bunch of the electrons are bound in core orbitals, and maybe they don't count, they don't run around, they just stay fixed. But there's some other atoms, that works perfectly well for sodium and for potassium. But what about for carbon? Carbon, makes diamond. It has 4 electrons in its valence orbitals, 4 electrons in its outermost shell. And in fact, it's an insulator. There are no electrons running around free, so why not? What's going on there? Why do we count 1 electron per atom? Why do you not count some electrons at all? So what happened to those other electrons? What about the sign of the Hall effect? Sign of RH, our Hall, the Hall coefficient. It's always supposed to have the same sign in Drude theory, also in Sommerfeld theory. It's always supposed to have the same sign. And we measured experimentally, well, we didn't measure, but it was measured experimentally, that in fact the sign comes out wrong sometimes. Another thing that's kind of interesting I didn't mention before, optical properties are different. Well, maybe why different? Why different? What I mean by this is that different metals look different. So, gold looks kind of goldish, silver looks kind of silverish, copper looks kind of copperish, hence the name. But tin looks kind of, lighter, and lead looks kind of darker. They look differently. They have different optical properties. They reflect different colors. Why is that? In the free electron theory, they should all look exactly the same. Another thing we didn't address is magnetism. Magnetism. In particular, things like iron are ferromagnetic, coming from the name for iron, that you can have magnetization not equal to 0 even when B equals 0. You probably studied this in your electromagnetism course. Why is that? The free electron picture would never get that. Finally, what about Coulomb interactions? Coulomb interactions. When we think about the electrons running around in the solid, they have a huge Fermi energy, 80,000 Kelvin. But if you think about the energy scale of the Coulomb interaction, it's just as big. The interaction of the electron with the nucleus, the nuclei it goes by, also 80,000 Kelvin, also a huge number. The interaction of the electron with other electrons that are running by it, also 80,000 Kelvin. We threw it out completely. We just treated these electrons as if they're a free gas, no interactions whatsoever. We only treated the fact they have Fermi statistics. To a large extent, all of these problems come from the same thing, that we're neglecting the same thing over and over and over again, and we're going to have to take more seriously one particular item. And that one particular item is that materials have microscopic structures, detailed microscopic structures. Atoms are stuck together in a particular way, frequently a particular periodic way, and that completely changes their properties, and that's what we're going to have to deal with for much of the remainder of the term. All of these things, to a large extent, will be sorted out once we deal honestly with the fact that the atoms are arranged in some particular way. The first thing we're going to have to do is we're going to have to understand why it is that the atoms actually stick together to begin with. And so starting the next lecture, we're going to discuss a bit of chemistry and chemical bonding. Just a really quick thing, how many people had A-level chemistry? Oh, that's pretty good. How many did not? OK, you're the lucky ones. Because you're going to have to unlearn a lot of the things that you know. Maybe you're not lucky. It's always good to learn things, even chemistry. But you may have to unlearn some of the things that you learned previously, because we're going to look at it from a more physics perspective. And I will see you Thursday. Thursday? Thursday? OK, Thursday.